Now we're going to look at capacitors in circuits. And of course, if we just had one capacitor in a circuit, so here's a battery voltage source, we put a capacitor in there. Initially, that capacitor acts like a short circuit. And I say initially because current will flow off of one plate onto the other plate until there is a potential difference here, and then this acts sort of like a resistor, and then it eventually acts like an open circuit when the voltage here and here are the same and no current will flow. What happens if I put multiple capacitors in a circuit? Well, it depends on how we hook them. We can hook them in parallel like this shows, or we could hook them in series, and we'll look at that in a minute. So we're going to look at the equivalent capacitance of a parallel circuit. Now, the charge that gets distributed to each plate on here, all of that charge had to come from the battery. So that's what this equation says. The charge that left the battery is equal to the charge that is distributed on each one of those capacitors. And so if we were going to replace those capacitors with an equivalent capacitor, it'd have to have the same amount of charge at the same voltage. But these are in parallel, so the voltage across any of them is the same as the voltage across the battery, right? It is still following the parallel circuit rule. So we do know that Q is equal to the equivalence capacitance times that voltage. But since Q is equal to Q1 plus Q2 plus Q3, and Q, remember by the definition of capacitance, Q is equal to C times V, we can go ahead and say, oh, well then Q1 is actually the voltage, which we wouldn't have to use volt 1 because it is the same voltage everywhere, times the capacitance on 1. And Q2 is the voltage capacitance 2. And so if we add those up, what we end up with is this equation. So the equivalent capacitance is the sum of the capacitances, and since we have a V on both sides, we don't actually care what the potential is. As long as we add up the capacitances, we have the equivalent capacitance. So you'll notice this acts a lot like resistors in series. So resistors in series, we add their resistances. Capacitors in parallel, we add their their capacitances in order to get the equivalence capacitance. For series resistors, or sorry, series capacitors, this is a little bit different. First, if you imagine this in the uncharged state, then everything here has a total charge of 0, right? We have conductors made of protons and neutrons and electrons, and the protons and electrons are neutral together. When we apply a voltage to this, what happens is, right, electrons start to flow this way and are pulled this way. So we get a charge separation, and the electrons that are pulled from here get distributed there, and because this is positive, it starts to attract some negatives, so electrons get pulled this direction. Those electrons had to come from here, so this plus Q and this minus Q have to be the same. This plus Q and this minus Q have to be the same. This plus Q and this minus Q are the same, and they attract as much as they are. So it turns out the charge on every plate has equal magnitude. So here, each capacitor has the same charge Q. Now, these are opens, right? Current can't actually get from one plate to the next. So the charge, like I said, lost by one is gained by the other. So these charges, this charge is also the total charge that left the battery. So the sum of the voltages across each capacitor must be the voltage of the battery, right? There is a voltage drop across here, V1, and a voltage drop across here, V2, and a voltage drop across there, V3, but this is a series path, so it must be the case that the voltage 1 plus V2 plus V3 has to equal the voltage of the battery, which would be measured at these 2 points, VAB. There's Kirchhoff's rules, and then the charge is all the same, and remember, voltage times capacitance is equal to the charge on the capacitor, and so if I want, I can say Q is equal to Q over C is equal to V, and so Q over C1 is V1, Q over C2 is V2, right? This is just another way of writing V1, V2, V3, and we can add those all up, and that has to get us the voltage of the battery, which is the equivalence capacitance. And so we factor out that Q And again, we can cross the Q's out, and that gives us this equation. 1 over the equivalence capacitance is 1 over C1 plus 1 over C2 plus 1 over C3. And so what we see is capacitors in series act like resistors in parallel. So resistors in parallel, capacitors in series, they have very similar equations.